Well, hi there. I'd like to say a few words about the common geometrical shapes that we find in the geological world. Keep in mind that the geometric configuration and the three-dimensional morphology of geological features are important in our understanding of their genesis and significance. By the way, I'm Robert Font. I'm a certified professional geologist and a proud member of the AIPG. Well, allow me to illustrate the point with some specific examples. What geological features could be represented by the mathematical functions that I'm giving you here? Y is equal to 2 times the absolute value of x, y is equal to x squared, and x squared over 9 plus y squared over 4 is equal to 1. Okay, let's take each equation at a time. The first one is y is equal to 2 times the absolute value of x. That could be indicative of the V-shaped valley of a young mountain stream or a chevron syncline. Now the general equation is y is equal to m times the absolute value of x minus h plus k. Now h and k are the x and y coordinates of the vertex, and m is the slope. In our case, the slope is 2. Young mountain streams are characterized by V-shaped valleys where the stream does not occupy the entire valley. Chevron falls have tight hinges and straight limbs. They result from compressive stresses that act on a sequence of beds of different ductility. Our second equation is y is equal to x squared. Well, that's the equation of a parabola. The general equation of a parabola is y is equal to a times x minus h squared plus k, where h and k are the x and y coordinates of the vertex of the parabola, and a determines how wide or how narrow the parabola is. Now, where in nature do we find these parabolic shapes? Well, in more gently folded synclinal structures, in mature stream valleys with existing floodplains, and in glacial valleys. I was able to take this picture. This is a classic U-shaped glacial valley near Glacier Bay, Alaska. Let's look at our third equation. X squared over 9 plus y squared over 4 is equal to 1. Now that's the equation of an ellipse with a major axis length of 6 and a minor axis length of 4. And you may ask, where do we find elliptical shapes in geological landscapes or in nature? Well, I can think, for example, of boudins. Boudins are roughly elliptical structures, kind of shaped like a sausage, that form by extension where a competent or rigid rock layer is stretched within a less competent, or if you will, a more ductile layer. If you look at the equation that I have given you here, I can tell you that elliptical boudins of similar proportions are described in Norway, where the competent rock, the boudin itself, is composed of amphibolite, and the more ductile strata are quartzitic schists. Where else in nature do we find quasi-elliptical shapes? Well, for example, in clastic sediment that has been transported. Here you see some quasi-elliptical cobbles, even a boulder. Well, I hope that I've been able to make my point. By the way, the picture that you see here is out of Le Petit Piton on the island of St. Lucia. This is a volcanic peak made out of dacite. The general equation of its current geometrical shape is y is equal to minus m times the absolute value of x minus h plus k. The minus sign in front of the m being the slope, means that the geometric feature points upward rather than downward. Well, that's it. Hopefully you have learned something. Take care. Bye-bye.